Given a curve, whether in R2 or R3, starting with any particular point on the curve, we can develop what's called an arc length function that'll give us the length of the curve as t increases from that point. Here's what I mean. Suppose we have here a curve in 3 space and a point P on the curve, and the curve is increasing in a direction here as t increases. For various values of t, the curve traces out, and we end up with successively, in this case, longer arc lengths, of course. And what ends up happening is we can express the length of the curve in terms of t. The way that's going to work is s of t is now going to be the arc length for a particular value of t is equal to an integral from a to t. A corresponds to the fixed point P on the curve. And then an expression for the arc length integrand, r prime of u in magnitude du, where du is associated with u. U is really just a dummy variable. So at the point we identified P, we would say that t equals a, and then for any successive values of t, we can generate an arc length using this integral. And this integral here is called the arc length function. From the fundamental theorem of calculus part 1, this implies that ds dt, so the derivative of the arc length function with respect to t, is equal to, fundamental theorem of calculus says if I differentiate an integral, I get the integrand evaluated at the variable upper limit. And so ds dt is equal to the magnitude of r prime of t. To see what this means, what we're saying is the change in arc length over time is equal to r prime of t. Folks, arc length is distance. This is distance divided by time. This effectively gives speed. It can tell us how fast a particle is moving along a curve. Formally, it's the rate of change of arc length as t changes. Furthermore, by using the arc length function, we can reparameterize a curve in terms of the arc length, and we're going to look at that now. We're going to find the arc length function from a point P, and then reparameterize a curve with respect to arc length starting from P. After that, we're going to find a point 4 units along the curve from P. Our curve is r of t is equal to e to the t sine of t I plus e to the t cosine of t j plus the square root of 2 times e to the t k. The point P is 0, 1, square root of 2. Now, one of the first things we need is a value of t that gives us the point P. Looking at x, 0 is equal to e to the t times the sine of t, and my first thought is that t could be 0 or pi, but really my first thought is t is 0. And then I'll just double check that looking at the y coordinate and the parameterization for y. 1 is equal to e to the t times the cosine of t. T equals 0 works for that equation as well. And finally, if t is 0, then square root of 2e to the t is square root of 2. So we get that the point P is associated with the parameter value t equals 0. Come to think of it, for the arc length function, that really should be a equals 0. It's a fixed point on the curve. Using the arc length function formula equation here, I would like for you to find the arc length function for this curve. Pause the video and come back when you're done. Differentiating to get r prime, we're going to use the product rule a couple of times. We notice that there's an e to the t sine of t for the I component, and when I use the product rule, I'm going to end up with factors of e to the t in both terms. So I'm going to factor that out, e to the t, and I'm left with the quantity of sine of t plus cosine of t for the I component. Likewise, for the j component, we have e to the t times the quantity of cosine of t minus the sine of t, all that times j. And then for the k component, our function remains unchanged. Square root of 2e to the t differentiates to square root of 2e to the t. Squaring each of these is going to give us a factor of e to the 2t. So I've factored that out of the work that we're going to see here. And then squaring the binomial sine of t plus cosine of t, and then squaring the other binomial cosine of t minus the sine of t, we end up with two instances of sine squared of t plus cosine squared of t. Those each become 1. The middle terms, 2 sine of t cosine of t and negative 2 sine of t cosine of t, subtract out. And then having factored out the e to the t, the square of the square root of 2 is of course 2. So we get for our magnitude of r prime of t, the square root of e to the 2t times 4. And that of course simplifies to saying that the magnitude of r prime of t is equal to 2e to the t. The arc length function is s of t is equal to the integral from our starting value of t associated with p, which is 0, to the variable upper limit t. Our integrand is 2e to the u du. Remember, u is a dummy variable. Really, I just need to make sure that these letters match. Integrating and then evaluating at the endpoints, we get that s of t is equal to 2e to the t minus 2. This is the arc length function for our curve starting at p. So here we have satisfied part of part A. We were then asked to reparameterize with respect to arc length. What that means for us is I want to express t, the parameter, in terms of s, the arc length. In other words, solve for t. S is equal to 2e to the t minus 2, which means that s plus 2 over 2 is equal to e to the t. So t as a function of s is equal to the natural log of the quantity of s plus 2 over 2. It just kind of turns the arc length inside out. The reparameterization is going back to the original curve. R of s now will be equal to e to the natural log of s plus 2 over 2 times the sine of the natural log of s plus 2 over 2, I, plus e to the natural log of s plus 2 over 2 times the cosine of the natural log of s plus 2 over 2j, plus the square root of 2e to the natural log of s plus 2 over 2 times k. This can of course be simplified. R of s is equal to s plus 2 over 2 times the sine of the natural log of s plus 2 over 2, I, plus s plus 2 over 2 times the cosine of the natural log of s plus 2 over 2j, plus s plus 2 over the square root of 2k after simplifying. This is the reparameterization of our curve in terms of arc length. And that reparameterization does it for part A. For part B, what we're looking for is a point on the curve that's 4 units along the curve from P. So we know the arc length is 4. Let's see how we can conceptualize this. What we need is T such that the arc length is equal to 4. And then really what we're after is R of that T value, and that'll give us the point that we want, right? It's the head of that vector. Reminding ourselves that the arc length function that we came up with was s of t, reminding ourselves that the parameter in terms of arc length is t of s is equal to the natural log of s plus 2 over 2. It follows that t of 4 is going to be the natural log of 4 plus 2 over 2, or natural log of 3. Putting that into r now, r of the natural log of 3, and I'm going to go ahead and simplify as we go, is going to be equal to 3 times the sine of the natural log of 3i plus 3 times the cosine of the natural log of 3j plus 3 times the square root of 2k. Therefore, the point on the curve 4 units from P is 3 times the sine of the natural log of 3, 3 times the cosine of the natural log of 3, 3 times the square root of 2.